0 do not exist. While here we compared the displacement, the monoclinic medium is more deformed as compared to the orthotropic medium. This is a conclusion part. References. Thank you, sir.
Thank you, ma'am.
Okay.
Any question from audience side?
Now, Dr. Sunit, you can share your screen and
Okay, sir. Yes, my PPT is visible, sir.
yeah. Please wind up as soon as possible.
Okay, sir. Topic is an extension of TODEM with VCOR approach based on Gini-Simpson index of diversity under fuzzy set, sir. So in this base, we had given the Gini-Simpson entropy, which is helpful to measure the in various result in pharmaceutical. Like the picture fuzzy set was introduced by Kyong and Krenwick, and we have used an application of opinion poll by using this proposed entropy. So this is in introduction. First we had given the concept of fuzzy set, which is just give the membership function. Later on, it extension is individually fuzzy set, which gives the membership and non-membership function. Later on, a picture fuzzy set, which give membership, non-membership, neutrality, and the rest is uncertainty. So these are
the come to the modeling part.
Okay, sir. This is the proposed entropy, and this is my proposed information measure, which I used over here.
Okay.
This is the proposed information measure, and this satisfies the properties of the picture fuzzy set. And later on, I use the VCOR TODEM approach. In this, this is the model which I used to solve the opinion method. Then extension of TODEM based on VCOR for picture fuzzy multi criteria decision making problems. This is the problem. This is the method which I use in this part. This is the VCOR method.
So please come to the conclusion session.
This is the example which I had taken for the 1000 people has been considered in survey. 3 people scored in party V1, and similarly 200 for P2. So in this way, I have proposed my model. So later on in the conclusion, these are all the mathematical formula I used over here. So this is the conclusion at the last. I compare it with some existing entropies. I just make the comparison with the existing entropies, and my proposed entropy shows the better result in comparison with the existing entropy. The ranking of alternatives are given in this part. So in the conclusion, in this paper, we conclude a new fuzzy information measure which is successfully introduced, validated in light of new proposed framework. And this, later on, we can do the extension of this introducing fuzzy set in Pythagorean. And if the Pythagorean is done, we use the Q-Rang method. And these are generally used in pharmaceutical sector. We can use in engineering sector, health department, insurance sector. And there are so many fields which we can apply our this entropy. Thank you very much, sir.
Thank you, sir. Any question from audience side?
Okay.
Uh,
now,
Yes,
Wank will share your screen.
Okay, sir. I'm just sharing my screen, sir. Yes, sir. Is it visible, sir?
Sir, they are asking, you can close. Wank will share the screen. Wank.
Okay, sir.
Wank, are you there?
Wank, you share your screen.
Okay, thank you, sir.
Yes, he is sharing. Wank is sharing, sir.
Okay.
So screen sharing again drop.
Yeah, Venk, start now.
Hello, Venk, your mic is not working. I think then you can do tomorrow. Okay.
Yeah, actually, it is a good idea.
Yes,
Yeah.
yes.
Now, hand Neha.
Okay. Yes, sir. Thank you, Neha ma'am, for giving me an opportunity to handle this session. Now over to you, and please continue the session.
Um, Thank you, Mr. Ban, sir. Thank you,
Thank
all of you. Thank you so much. Now, we're starting the next keynote session. Our next keynote speaker is the Professor A.E. Cardenas Barron, the co-researcher Optimization Data Sciences, Technological, de Monterrey, Mexico. And the chairperson for this session is Professor Neeta Shah, ma'am, Department of Mathematics, Gujarat University, Gujarat. Now, I would like to invite hello. Now, I would like to invite Dr. Himani ma'am to give a brief introduction of Professor Barron. Over to you,
Yeah,
ma'am.
yeah. Thank you, Neha. Good evening, everyone, and good morning, Barron sir.
Good morning.
Good
Nice
morning,
to
sir.
hear you. Good
Yeah,
morning.
same here, sir. So I welcome you for this talk. So Professor sorry, Professor Leopoldo Eduardo Cardenas Barron is a very glorious name in the research areas of inventory theory, optimization, and supply chain. And he received the BS degree in Industrial and System Engineering, the MS degree in Manufacturing Systems, the MS degree in Industrial Engineering, the PhD degree in Industrial Engineering, and he has obtained all these degrees from Tecnológico de Monterrey, Mexico. In 1996, Professor Barron joined the Industrial and System Engineering Department at Tecnológico de Monterrey, where he was appointed as assistant professor in 1997, associate professor in 2001, and professor in 2007. At present, he is an eminent researcher in the field of optimization and data science. His academic research, leadership, and at Tecnológico de Monterrey has been awarded with several awards, such as Teaching and Research Award in 2007, Romulo Garza Prize for Research and Technology Development in 2011, and award to professor who left a mark from the community of former students of Tecnológico de Monterrey in 2013. He is a member of the Mexican Research National System since 2015, and he is also co-author of a book related to simulation, that in Spanish. He has published more than 150 research articles in reputed journals. There is a huge number of citations to his work, that is more than 6,500. And I'm happy to share that besides that, He is extremely down to earth, cordial, and big-hearted person who is always very inspiring to his students and colleagues. We are much fortunate to have him with us today once again to share his knowledge at this platform. A very warm welcome to you, sir. Over to you.
Okay, thank you. Thank you for your invitation. My question is, can you hear my screen in full screen?
Yeah, sir.
Yes, sir.
Okay. Okay, I will start.
Uh,
Okay, thank you very much for inviting me to give a talk to you in this international conference on sustainable development, modeling and optimization. I will present you an inventory model which rotates for growing items and price sensitive demand under carbon emissions considerations. This is my research team for this research work. My co-authors are Cynthia Grisel de la Cruz Marquez. She is here, she is connected now. And the other co-author is Budadev Mandal. At the present time, the customers have become more environmental and quality consciousness than before. In this context, it is needed that firms build and apply inventory models that take into account sustainability issues. Additionally, there is a kind of items that is required to feed them until to a goal weight is achieved in order to slaughter and vend to customers. These items are called growing items. In this direction, this paper introduced an inventory model for growing items with price-sensitive demand, considering carbon emission as a tax carbon and shortage with fully backordered. The proposed inventory model computes the optimal values for price, lot size, and backordering level that maximize the expected total profit. The first model related to growing items was published in 2014 by Risai. 2 years after, in 2016, Zhang et al. Published another paper. In this table, you can see the main characteristics that we need to show: price-dependent demand, type of price-dependent demand, shortage, type of shortage, imperfect quality, carbon tax, type of objective function, and what kind of decision variables they optimize. Sebastian in 2018 published 3 inventory models related to growing items also. You can see that in the first column, all the papers, Sebastian, Kalipur, Sari, and Nobil et al. doesn't consider.
Sorry, sir, to disturb you.
Yes, tell me.
Sir, please shift the next slide also.
You see?
Yes.
You see this slide?
Only title slide is there, Professor Barron.
Okay, only title slide. Okay, I will check why it's not working. Now you can see the.
No, sir.
Still
no
title.
Okay, I am chair. I will stop sharing. I will start again the.
Yes, sir.
Okay, thank you. I will share. Can you see? Can you see?
No,
No,
sir.
sir.
Now it is coming. Just wait.
It's coming?
But go to the slide number 4, sir. It is just title slide.
Okay. You can see the second slide?
Yeah.
Yes, sir.
Okay. Okay. This is my research team. My co-authors are Cynthia Grisel de la Cruz Marquez. She is here now, and Budadev Mandal. I talk with you these kind of things that the clients are become more environmental and quality conscious than before. In this context, it's needed that firms build and apply the inventory models to take into account sustainability uses. Additionally, there is a kind of items that is related to fit them until to a goal weight is achieved in order to slaughter and vend to clients. These items are called as a growing items. In this paper, we introduce an inventory model for growing items with price sensitive demand considering carbon emissions as a cap tax, as a tax carbon, and shortage. The shortages are fully backordered. The proposed inventory model computes optimal values for price, lot size, and backordered level that maximize the expected total profit. This kind of growing items inventory model start with the work of Resai in 2014. Resai proposed a paper for growing items 2 years after Sang et al. In 2016 proposed another inventory model with growing items. And the first column showed the price-dependent demands if the research works contains this characteristic. Also, if the works contains this characteristic, also which kind of price-dependent demand they are using, if the paper contains shortage, and which kind of shortage they are considering, imperfect quality also, and carbon tax or not, and type objective function, maximization or minimization, and what kind of decision variable they are optimizing. In 2018, Sebastian published 3 inventory models that are related to growing items. But you can see in the first column, not all of these inventory models consider price-dependent demand. Also, only one, Novit et al., consider a low shortage, and also type of backordering for Nobil et al. In 2019 is full backordering. They don't consider imperfect quality. Here are more inventory models. All are very recent. All are from 2019 and 2020 and 2021. All these research from Sebahane and Tunji, the reference 40, 41, and 43 are for 2019, and Sebahane and Tunji 43 is for 2020. These are 2 works. You can see there are one work with price-dependent demand like exponential, Sebahane and Tunji, reference number 43. And this is kind of the decision variable that they optimize, like selling price, cycle time, etc. The more recent work are from 2020 and 2021. This work that you can see in the slide are for 2020, the model de Garay and Almehadawe, Hidayt, Mokatari, and Nishandi. You can see Nishandi consider shortage in full consideration, also consider imperfect quality, but do not consider carbon emissions. They optimize order quantity in minimization costs. The last papers are for 2021, Alfares et al., and also Sebahane and Adetunji, reference 51 and 52. In general, this research work proposed inventory model for growing items with price-dependent demand, with polynomial price-dependent demand function. We consider shortage with full backordering, and also we consider imperfect quality. We consider also carbon tax. We optimize selling price, ordering quantity, backordering quantity, cycle time. This is the notation. P is for scale parameter for price-dependent demand, rho sensitive parameter for price-dependent demand, and demand power index, B selling price of imperfect quality items, and K is for setup cost, H for holding cost, B for shortage cost, C, feeding cost, P for purchasing cost, and Z is for inspection cost. Theta is the carbon tax rate, and EC is the carbon emission cost. K with cap is the amount of carbon emission generated during the setup process. H with cap is the amount of carbon emission caused by holding items in warehouse. And C with cap is amount of carbon emission generated during the feeding period. And P is the amount of carbon emission made during the purchasing activity. And C with a cap amount of carbon emissions created during inspection process. R is the inspection rate, alpha is the asymptotic weight of each item, beta is the integration constant, and lambda is growth rate. X is the percentage of slaughter items that are in perfect quality. Expected value of X is represented with this expression, and 1 minus expected value of X is expected value of percentage of perfect items. W0 is the weight of a newborn item, W1 is the target weight of a grew item, and WT is the weight of the item at time T. T1 is the growing period, T2 is the inspection period for backordered quantity of the previous cycle, and T3 inspection period for J, W minus B units of weight, and T3 is the inspection, T4 is the consumption period of perfect items after inspection time, and T5 is shortage accumulation period. We optimize 3 main decision variables: the order quantity, represented by J, Y, and B is the backordering quantity, and S the selling price. We have 3 dependent decision variables: capital T, cycle time; capital Q, total weight at the beginning of growing period; Q T1, total weight at the end of the growing period T1. There are some functions that we are using in the modeling. D in function of S, the demand price dependent, and WT is the growth function, JX is the probability density function of the percent of the imperfect items, TPU is the total profit in function of the 3 main decision variables. This is the graphical representation of the inventory holding behavior through time. At the beginning, we buy, I show in this graphic 2 complete cycles in order that you see the continuous cycles through time. But now I will expose in detail each cycle. At the beginning, we buy newborn growing items, animals like chickens, like pigs, like cows, like any animals that you buy, and then you buy Y animals, and each of them has an initial weight of W0. This is the total weight at the beginning of the period. Then we feed the animals onto a target. The target is that each animal obtain a weight of W1. Then this is the final total weight. We model the feeding period as a logistic function. During T1 is the feeding period. When we reach the target total weight at the end of the feeding period, we start immediately to inspect the B backordering units in order to deliver it to customers immediately. And then after the inspection of P units, we drop vertically the inventory level. And then we sell the product. During the inspection time of the backordering level, we don't sell. We start selling inventory, sell the inventory here in this point. in T2. And these are the areas A1, A2, A3, A4, A5, and A6 for the inventory level in order to compute the positive inventory units and the backordering area. And then we are selling units. And also, it's important to mention that we are continue inspecting the whole lot of Q1. And then after we remove all imperfect quality items. Here is the all imperfect quality items. And then we reach, after some time, we reach the level 0 and then start accumulate the backordering levels for next cycle. And through time T1, the items are growing according to logistic growth function, which relates the weight of the items with time using 3 input parameters. These input parameters are alpha, beta, and lambda. This logistic function is the form given by equation 1, and we can solve this equation. We represent this equation for t equal to t1 with this expression 2, and we solve this expression 2 for t1. We obtain the time of the duration of group period, which is calculated by equation number 3. This is the equation number 3 for calculation the t1. T2 is easy to obtain, is B. We expect P units. We divide the B units in the inspection rate, the total inspection rate with equation 4. After the inspection of backordering quantity, we continue the screening process. At the total weight, we remove the big units. I will to mention here. Here is we put in not in animals. We put in kilograms, and here B is kilograms. Also, we can remove the kilograms of the backordering that we deliver to the customers. And obviously, divided by the inspection rate, this is the time for T3. After the inspection T3, the imperfect quality items are withdrawn from the shortage and sold. And then now on-hand inventory contains only perfect quality items. We obtain the T4 as a expected value because depends on random variable that is the percent of imperfect items, and with this expression, and shortage accumulation period with this expression. Finally, we obtain the expected value for the cycle time that is given with this expression, equation 8. That is the summing of equation 5, equation 6, and equation 7 represent T3, T4, and T5. We compute the expected total revenue as the revenue for the perfect items and revenue for the imperfect quality items. We assume that imperfect quality items we can sell in a whole lot, obviously in a lower price. And the expected total cost is computed as a sum of the purchasing cost, setup cost, feeding cost, expected holding cost, inspection cost, backordering cost, and expected carbon emission cost is given by this equation 10. With these two expressions for total revenue and total cost, we obtain the expected total profit given by equation 11. At the beginning of each period, the company buys Y newborn items at cost of P. Therefore, we calculate the purchasing cost given by equation 12. This setup cost is very simple. It's simple. The ordering cost or setup cost K given by equation 13. The feeding cost is calculated with this expression given by equation 14 is the feeding cost C multiplied by the quantity of animals by the integration from 0 to T1 of the logistic function of the growing period, during the growing period. Now we calculate the holding cost. This is the holding cost. We compute the areas for the positive inventory, and then we calculate with equation 15 the total inventory cost, with this expression, equation 15. Also, we have inspection costs. We expect this calculation with this expression 16. Shortage costs with expression 17. And carbon emissions. There are many works that suppose carbon emissions that companies generate through many activities like transportation, warehouse activities, etc. Here we consider that we cause carbon emissions during purchasing activities, because when we purchase, we transport the products as during setup, during feeding. Also, the animals generate carbon emissions. Holding inventory also we consider in this process, inspection, etc. The carbon emissions, here we consider carbon emissions generated by purchasing activities, setup activities, feeding cost process, inventory operations, and also for inspection process. All are given by equation 18, 19, 20, 21, and 22. Therefore, the carbon tax, theta, is one of the well-known mechanisms imposed by government regulation as a penalty. Here we compute the carbon emission cost per period given by equation 23. The expected total profit, we compute the expected total profit. We use this expression, the expected total profit divided by expected cycle time. And this is the final expression for the expected total profit per unit of time. This is a non-linear, highly non-linear expression function in the three decision variables, y, b, and s. And we consider a polynomial function given by d in function of selling price with this expression p minus rho x to power n. And this is the expression. We substitute this expression, and then the expression is the expression that we need to optimize. This is the optimization problem. The optimization problem consists in maximization of the expected total profit per unit of time, where the set omega is given by this, where y is greater than 0 and number of b backordering is in this expression, and selling price has a lower bound of purchasing cost and upper bound of maximum selling price given solving the polynomial function. In order to avoid a negative demand, we need to put the upper bound. Then the objective is to find the optimal values for J and B and selling price that maximize the expected total profit. And we use the classical differential calculus to optimize. The necessary conditions that we need to satisfy is the first derivatives for each decision variable. Also, we need to prove the optimality of the total profit per unit of time. We use the classical Hessian matrix, and we consider the determinants for this Hessian matrix. We need to determine H1 less than 0, determine H2 greater than 0 and determinant H3 less than 0. And the first partial derivative for selling price, no, for the Y number of animals that we need to buy is given by equation 27. This is the first derivative with this expression. This is the first derivative with respect to backordering level given by 28, equation 28. And this is the first derivative with respect to selling price given by equation 29. By solving simultaneously equation 27 and equation 28 for the decision variables y and b, we obtain these expressions, dirty and dirty one. This expression for number of animals that, or growing items that we need to buy and the backordering quantity. And in order to optimize, we propose the following algorithm. Step 1, we provide the input parameters. And step 2, compute the selling price, the order quantity, and the backordering quantity by solving equations 29, 23, and 29, dirty, and dirty one. If the optimality conditions are satisfied, then go to step 4, else go to step 8. Step 4, if selling price is between the lower bound and upper bound, then go to step 7. This is very important because we are solving a equation for selling price, and the solution for this expression, I will show this expression. This is the expression that we need to solve numerically. The solution can be above of the lower bound. Then obviously this is solution is not permitted. Mathematically is right, but with any value above upper bound, we produce a negative demand. This is not feasible in real world. And if the selling price is greater than this upper bound, then we set the selling price at the upper bound. Then determine the order quantity with equation 30 and the backordering quantity with equation 31 and go to step 6. Else set selling price at the lower bound and calculate order quantity with equation 30 and backordering quantity with equation 31 and go to step 6. Step 6, compute only the total expected total profit per unit of time given by equation 25. And finally, we report the solution for the 3 decision main variables and total profit per unit of time and stop. This is the algorithm. Our model is a general model because contains several inventory models previously published, like the Sebahania and Tunji. We propose an improved inventory model, Mada-Haber, Chan and Ho, Chi, Silver, and the traditional EOQ models with and without shortage. The first special case is very easy to identify when n is equal to 1, means that the product has a linear price dependent demand. We obtain this expression very easily here. And the other special case is when shortage and carbon tax rate are not considered and the demand is not dependent on price. That means that B is go to infinity, theta go to 0, and rho go to 0. Then we obtain a new version from Sebahania and Tunji. It's an improved version because the original published paper by Sebahania and Tunji has an error. And we improve this error, we obtain a better expression. Other special case is when shortages are permitted, carbon tax is not involved, demand is not dependent on price, then the products are not type of growing items. Thus, the feeding process is not incorporated. This is the condition for B, theta, rho, and C. Then the inventory model of Chan and Ho is obtained with this expression. And when shortages are not allowed, carbon tax rate is not taken account, the demand is not dependent on price, and products are not type of growing items. That means B go to infinite, theta go to 0, rho to 0, and C go to 0, then we obtain the Madan-Havers inventory model. This is the Madan-Havers inventory model. When shortages are not tolerable, carbon tax is not considered, the demand doesn't depend on price, and the goods are not type of growing items, and the inspection rate is sufficiently large, we obtain the model of Chi and Silver given by this expression. And obviously, when shortages are allowed, carbon tax is not incorporated, demand is not dependent on price, products are not type growing items, and the products are of perfect quality, we obtain the classical inventory model, EOQ inventory model with shortage, given by these two expressions for lot size and back-ordering level. When shortages are not allowed, carbon tax rate is not taken account, the demand doesn't depend on price, the goods are not of type of growing items, and these are of good quality, then we obtain the classical EOQ model of Harris. This is the expression. It's important to remark that the inventory model that we propose in this research does not reduce to the classical inventory model of imperfect quality items proposed by Salameh and Haber, and one extension of the Salameh Haber proposed by Gui et al. Because both inventory models has a flaw or has an error. That errors were corrected by Madan-Haber and Chan and Ho. Therefore, our model reduced to Madan-Haber and Chan and Ho. Now we discuss a numerical example. The numerical example data is shown in the screen. We have any value for all the input parameters. The percent of imperfect quality items follow this uniform function with these numerical values you can see in the screen. And this is the graphical representation of the concavity with total profit with respect to two decision variables, with respect to Y and B, respect Y and selling price, respect with B and selling price, etc. This you can see the concavity of the function. This is the comparison table with the solution of the four inventory. The original inventory model, I showed that there is a flaw or error in this inventory model. We improved this inventory model. The second column is the solution for the improved version of the original Sebahane-Adintuji model. And our model obviously permits to optimize the selling price. This is the solution for the selling price, total profit are better for the two previous, for the original, for the improved. Also, our model, we can put as an input the selling price, because Sebahane-Adintuji model has as an input value the selling price. If we consider as an input value, also we obtain better result than the original published papers. Finally, I will show a slide with a table that shows the sensitivity analysis of the key parameters of the inventory system in this form, what happened about the decision variables when the parameters increase? What happened when the parameters increase? For example, if parameter H increase, the lot size decrease, accordingly increase, and selling price increase, and total profit decrease. This is only one example to explain. This is my presentation. I hope that you enjoy. I finish now, and thank you for your attention.
Good morning, Professor Barron.
Good morning.
I have, in fact, it was very interesting lecture, incorporating good number of factors. First one, growing items, then carbon emission, back order. So 4 components are playing a vital role in optimizing objective function. So I enjoyed, and I can say that almost all attendees must have enjoyed this lecture and will get some hint or motivation to go for something new contribution in this area. So I invite questions from the attendees.
Good morning, sir. Is there anyone who'd like to ask any question?
So it seems that there is no question, and that proves that the presentation done by Professor Barron was so lucid that it got inherited by attendees. So thank you, Professor Barron.
You're welcome. It's a pleasure, an honor to be here with you.
Yeah.
Thank you for your invitation. Nice to see you again, Dr. Nita, Himani,
Thank you, sir.
Saxena, Dr. Chifra Singh. It's a pleasure for me to be related with you, also with Dr. Yadav.
Yeah.
I consider all of you very good researchers in the world, in the inventory field. You are the best. Thank you.
Good morning, sir. Umakant
Good
speaking,
morning.
sir.
Okay, nice to see you, Umakantu.
Okay, sir. Thank you.
So much, sir. Thank you so much, sir, for this productive lecture. And now I would like to invite. Hello. Now I would like to invite Dr. Monica to provide a word of thanks. Over to you, ma'am.
Monica, unmute
Dr.
karo.
Monica Vishnani, are you there?
Monica, unmute yourself.
Am I audible, sir? Am I audible
Yeah.
now?
Now you are audible.
Okay. A very good evening to all, and good morning, Professor Barron, sir. I'm Dr. Monica Vishnoi, member of the ORSI Meerut chapter, and it gives me immense pleasure to deliver the vote of thanks for second keynote speaker in the International Conference on Sustainable Development, Modeling and Optimization, organized by the Operational Research Society of India, Meerut chapter, with the collaboration of the Bharati University Meerut and Vardhman College Bhutan. Now, on behalf of the entire organizing committee of this conference, first and foremost, I would like to thank our special guest of this session and the second keynote speaker, Professor Dr. Leopoldo Eduardo Cardenas Barron, sir, for enlightening us with his knowledge. Thank you so much, sir, for your informative session on inventory model on carbon emission, which is a need of the society in sustainability development. Now, I'm sure that participants must have benefited by your work, sir. It will be very helpful in their research in this field. Please accept our sincere thanks, sir. Your knowledge always inspires all of us. Thank you so much, sir.
Thank you so
Now,
much,
I
Professor
would like
Barron.
to.
Yes.
Thank you.
Now, I
Yes,
would like